Okay, hi everyone. We're talking right now about the origin and the evolution of electric computation. And, we'll start with a pretty familiar mechanical solution. This kind of tool was used thousands of years ago to help people, solve more complex math problems. And I think the culmination of mechanical calculators culminated with this device here, which took the inventor about 30 years to perfect. And here's what it looked like. And we'll go through real quick how it worked. And it's really nothing more than just a series of interconnected gears, dials, and it was all built in such a way and woven together that you could just you could input your calculation parameters, and all you have to do is turn this handle. It would move all the gears and all the other gizmos and gadgets in there, and it would turn these dials here at the end. It would give you your output. And this here was ready in 1850, and I think that's a pretty amazing capability given how long ago that was. And why was there this human effort in the first place to build these automated systems? And it's because originally we did need a number of complex equations. We needed a number of tables that recorded the results of complex equations, and these were in demand. So originally it was a number of people who would hand compute all these values by hand, and they would publish them in these very large volumes. And this had severe limitations, or pretty quickly reached its limitations. I mean, one, the person computing this could have made a mistake, but two, if you just wanted to combine some of these numbers, or if you wanted to combine different types of tables or fields of study, you'd still have a ton of work to do. You have to do it manually. And so there was a strong need to automate these complicated equations, complicated processes. And there are two things really that brought us to the computer, which is Boolean logic and the telegraph. So Boolean logic or Boolean algebra, it really was built around supporting philosophy and to help dissect and analyze arguments. And it was really just a framework to evaluate arguments, like this one here, which is just the statement, "It is raining." It gave you a way to evaluate it, considering prior information, and then current conditions, what is true and what is false. And you could take the same approach and you could organize, very complex arguments. You could boil the whole argument down to just zeros and ones, trues and false. And this was binary, and this was just a useful way to view arguments. And then second, in the 1930s, this technology had matured that gave us long distance communication, and we became familiar and experienced with zeros and ones, and found that they're easy to make using electricity. They're easy to store. So we became very familiar with zeros and ones. And that led us to the vacuum tube, which was just a way to use electricity to make a zero or one. So it's what the vacuum tube was. This red coil here in the middle is a heater. And when you turn power onto the heater, so in this case the power is on, you see the red lines, it would heat up this cathode, and it would allow electrons to flow from the cathode to the anode. And in essence, when you didn't have power, electrons would not be flowing, the gate was closed. When you did have power, the electrons could flow and the gate was open. So this was closed, no power, it was off. This was, I might have said that backwards. So this had no power, the circuit was off, value is 0. This one, once you provided power, the gate closed, circuit was on. So you could use electricity to get zeros or ones. And you can arrange these vacuum tubes to mimic Boolean logic. So here's an example of vacuum tubes in an AND gate. So in this case, you would need both inputs to have the power turned on to them, and that would give you an output of 1. I think it's the other combinations here that you can see. And then similarly, you can make other arrangements. This is the OR gate. We have AND OR gate, and there are a number of number of common gates, and these are the input and output tables, given their configuration. And then there's a common symbology that represent these gates. And really, there's all types of ways you can combine and use these concepts and get more efficiency. So this is an AND gate for all four. And you can see here at the end, you need all four of these to be on in order for your output to be 1. So the first computer was really just electric calculations with zeros and ones. So we're going to walk through an example of how it did this. And the first step is you have to translate the function into pure binary, into zeros and ones. And this was usually done with some kind of standard representation of numbers using binary sequences. So in this case, 4 is 0, or is 1, 0, 0, and 3 is represented by 0, 1, 1. And then this again, 4 would be an on circuit, and in early computers you would just flip a switch and you could tell it was on because it would also light up a light bulb for you. And then same thing for the input of 3. And we take these two inputs, we'd run them through a calculation, and we get some kind of output. And then once we had the output, we have to translate it back to our answer. So we're going to feed these two inputs into the computer. And this is the Boolean logic would be arranged to take us through this process. So first we're going to in this addition problem we're going to add 1 to the input. We're going to get an answer, we're going to get an output, we're going to record that, and we're going to also record how many iterations that we've done. And once we reach the end of this cycle, we're going to check the number of iterations we've done against the value of input number 2. And so we haven't reached the value of input number 2 yet. We're not done with the addition problem. So we go back to the beginning with the new output, and we repeat the process. And we're going to keep checking the number each time, checking the number of increments each time until we know that the number of increments we performed is equal to the number that we need to add by. And this is all done with binary, zeros and ones. So, and we're not going to do all this. I'm just going to walk through just a simple example. So if we're adding 1, we're starting off with this input. We're starting off with this input 4, the number 4, which is 1, 0, 0. So powered on, off, off. So this would be 1, 0, and 0. And you can tell as we add 1 in terms of binary to this last binary representation here, every time we're adding to this, it's either we're changing either from a 0 to a 1 or a 1 to a 0. So what we need here is to pass this third binary representation, and we need to combine it with the power supply, which is going to be on, and we use an XOR gate. And it has this arrangement. So if the power is on, which it always will be, it's going to be a 1 or a 1. And if the third binary is a 0, it'll flip to a 1. And if the third binary is a 1, it'll flip to a 0. So that will allow us to add 1 for each iteration. And it would be similar logic, similar, maybe more involved arrangements of Boolean logic to take us down the other binary representations, but it's the same concepts, and Boolean logic is what performs it. And then after the first iteration, we're going to record the results from that iteration. And initially, this would be just like a circuit that would open and close, turn on lights. You could look at it, you could see the iteration was complete, you could see the current value, and then we'd capture the number of iterations that we'd done. Again, it would be some kind of feedback to let you know that iteration is complete. And then we, using more Boolean functions, we'd be able to route our pathway, our process back, and we could check the counter result versus the input 2 result, and if they're not the same, then we're just going to go back to the beginning. We're going to take the recorded result this time instead of input 1. We're going to take the recorded result, and we're going to run the add 1 iteration again. And after we've done this 3 times, our counter here, the value of our counter, is going to match the value of our input 2. That means we've added 3 times. And now the recorded result is also our answer. We can see it's 1, 1, 1. So we look at our chart and we can translate that back into the number representation, and we can see that 4 plus 3 equals 7. So the first computer was nothing more than just an arrangement of vacuum tubes to perform these cycles of Boolean logic, and it was all zeros and ones, and it required working memory in order to complete these cycles. And this is a picture of the ENAC, just a ton of vacuum tubes, and this was essentially the first large computer. 18,000 vacuum tubes, and all these wires that you see here connected, they could be unplugged and plugged back in, and then let you change the Boolean configuration. So it was very adjustable depending on what you were trying to accomplish. And then punch cards replaced switches and bulbs. You could pack a lot more information into them. They're a little more human readable, a lot more efficient. Transistors then replaced the vacuum tubes. They performed the same function. They were just a lot smaller and required a lot less energy. And then magnetic tape came to be. It was used to both record and then also read whatever our working memory was at the time. Just another way to record zeros and ones, just faster, more accurate. And then we had silicon chips, which replaced transistors, and that opened up the door also to integrated circuits, just very tiny chips, and capable of running billions of iterations. Billions of these cycles could happen every second, given the amount of Boolean logic that could fit on that chip. And then we also had, the long-term memory you can see here, the floppy disks, the DVDs, and these were just, again, a much more efficient way, a different way to store zeros and ones and make them accessible to the computer during its iterations. And then we also introduced just, human-friendly elements into our inputs. Keyboard, we had the mouse was invented. We had standards that were invented, that, the universal language to translate binary into certain letters. And this is a look at one of the first binary standards. This is what a string of all zeros, for example, 7 zeros in a row represented null, or 7 ones in a row represented the delete function. And then finally, we had a process at the output where the computer would translate the output, all those zeros and ones. It would translate those into pixels that we could see and just understand a lot quicker. So the computing power that we know of and the computing capability has increased astronomically, but still the functionality behind it is essentially the same. We have an input, zeros and ones, and we have an iterative computational cycles based on Boolean logic, working memory. And then we have a human readable output that helps us understand those zeros and ones just in a way we can make sense of it.